Hello everyone. Today, welcome back. Today I will be talking about projectile motion, part one. We will be explaining what is a projectile in a very abstract way, in a simple terms, and then we will do some approximation to tackle the problem such that is easy to follow, but it will give us the basic for then complicate it a bit more in lesson number 2 when we will add back some of the complications we are neglecting now. So starting from the beginning, so we call a project anything that can be flung through a vacuum or a fluid. So we no particular shape in mind. Anything that can be thrown is a project. In fact, the word projectile comes from the Latin word projectus, which means to throw forward or expel. So as I said, we will start with some approximation. I will tell them in a sec, but first let me give you an idea of what I mean by projectile. So usually if you think about a projectile, you have an idea of something of this shape, all right? Some cylinder with some pointy and rounded top. This is a projectile usually used in combat and war. We don't like those examples, but of course in history this is not the first things that we invented. At the beginning we were throwing stones, so maybe something like that. And then, so as you can see, there's a quite of evolution from shapes between a stone and a current projectile. Of course, there is quite a bit of a difference you can understand when these two objects go through air. All of the engineering that is done to come up to this comes from the fact that they study the turbulence on the surface of the projectile, so the drag force of the air and things like that. So for this video we are neglecting those one, and by the way we can approximate all of these shapes with a sphere, which we will be tackling in the next video. But even more so, we can even shrink down the sphere to a point, okay? To a point with a mass m. So this will be our projectile. A point with mass m, for which we are not going to consider the shape and the effect of air or water or any fluid that is thrown through. So this is an initial consideration I want to make. We will tackle some of those aspects in future slides. So next, we need to always consider about the forces that are acting on an object to understand the motion of an object. Okay, so first thing is to consider is that we think about flinging and throwing a projectile by being on a surface of a planet, suppose Earth for simplicity, but this would work on any habitable planet. Anyway, the gravity will then be the usual small g, which is an approximated value by 9.81 meter per second square, all around the Earth. Of course, by doing the approximation, we are neglecting the curvature of Earth or the fluctuation in density or altitude or any other complication that we might touch upon in another lesson. But for today, we're considering flat Earth with constant gravity pulling down, and I will show you in a sec what I mean by that. Of course, we said we were not considering turbulence of air, so there won't be any friction, there won't be any effect on our projectile. If you are familiar with any sport that involves throwing balls with different shapes, or even other sport where you throw objects like darts or things like that, you will notice that any sport has its own particular surface shape, and those surfaces are made on purpose to give rise to some specific effect that are specific to the dynamic of the sport itself. Okay, we will neglect all of that, maybe we will do, I don't know if we will be able to do an example of a real object. Maybe yes, we'll see. But for today, we are neglecting turbulence and friction of air. We will, as I said, we will then approximate as an idea as an extra force that we can add easily. It's a phenomenological force. We will basically condense all the turbulence effects of air with a single coefficient, the drag coefficient, which basically is a friction coefficient, which will impact the motion of our motion projectile. So just to summarize what I just said, we have somebody, so we have flat Earth, so the pull of gravity is constant and uniform. So this is the force of gravity that is pulling the object downward, and is mg, the force of gravity mg. So as you know, when you are on a curved sphere, the force of gravity pulls towards the center of the Earth. So technically speaking, it's not uniform, but the projectile is very small compared to the radius of Earth. We are very small compared to the radius of Earth. So in our approximation, we are very small. So the Earth is considered flat. The object is flinged towards the in front of us with certain initial conditions that we will talk about later. So this is what about first we said the Earth is considered flat. There is no air at the moment, so we will give some oxygen, O2, to our guy, some mask of oxygen to breathe in order to fling the stone or fling the projectile, which by the way, as I said, is considered as an object of mass m. Okay, with this in mind, we can yes, the drag of air. When we will add back air in the system, there will be some particles of air, we don't care. There will be some molecules, whatever, and they will be considered as a uniform fluid, which will act with a force that depends on the velocity of the object, and a coefficient gamma, which is the friction coefficient, and this will be the drag force, which is by the way the same that applies when a plane is flying, right? When a plane is flying, you have a drag force, and then the pull from the wings from the behind, and the gravity, and then the thrust of the engine. In this way, we have the thrust, which is our mechanical force to fling the object. If you are using a hand, the drag will be the air, which we can consider uniform, and the pull of gravity is always there. And okay, so bearing this in mind, we will have to set up some initial condition, and as I said, we will have to make other assumptions, throw away other assumptions. As you can see, it's a very simplified model, but to describe something very simple, we need to go through those assumptions. So first of all, we are not going to describe what is the actual dynamic or physics that impart the motion to the object. Okay, suppose you're flinging an object. Of course, depending on how you do it, the twist that you do to the object, the speed, the torsion, any little detail will be effectively the trajectory of the object. And maybe we will touch upon some of this in the another video. Or if you think about a gun, as you know, the inside of a gun is threaded in order to impart some spinning on the projectile. So as I said, we will neglect all of this, and we will just consider an initial projectile with some velocity in some direction and in some position. We don't care who gave and what gave that velocity and how it happened. We just know that there is an initial velocity and initial position for our object. And then we will draw some force diagram and then make some conclusion. Setting out the initial condition, we said, so I just to let you know, if you, of course, if you think about a real object, if you impart the rotation to the object, it might curve, as we will see, so we will neglect that. If we impart this kind of shape on inside of a gun, for example, and this is a gun, very badly drawn, but suppose it's a gun, the project will go outside with a spin as well, which helps to reach longer distances. So those things will be neglected. Even if you think about golf, the torsion of if you think about tennis or any racket sports, there is a specific technique to throw the ball, okay? And that motion, whatever it is, we will neglect, okay? So we will neglect all of these motions, and we will just think about an object mass with a velocity in some direction, v, and that's it, and position, x, okay? So these are interesting engineering and physical problem, but too hard to tackle for now. So we just don't think about those. But bear in mind that they are there, okay? Because reality is way more complex than what we are describing here. So okay, so now let's do some math then. So we have an object. Which has a velocity, initial velocity v0 with some angle with respect to a coordinate system, okay? The coordinate system is 2D at the moment. We are we can neglect, okay, let's do it completely. So we have x, so this can be z, this can be x, this can be x, and this can be y. Okay, so we only consider the one plane to simplify the math, so we will consider the z-y plane, this plane here, and nothing happens in here, nothing happens in this plane, okay? So we can trace out this plane here, and we will only consider xy plane, because we can always, if as I said, the motion is not, if there is no air and we don't consider rotation in the object, we can simplify the motion in just 2D. It could be 1D if there were no gravity, for example, okay? Now, as we said, there is only one force acting because there is no drag force of the air. So the only one force is a vector mg, which is pointing in the z direction, which is written like a vector z, which is in the direction z. And the motion is, the position is x0. Okay? And this is the vector to describe the motion. I just don't draw the whoever thrown the object anymore. Okay, this is the initial schematics. Okay, so what happened next is that two things. We need to write equations of motions in the two directions, z and x. Okay, because we know that F is equal to ma, which is the Newton law of dynamics, and then it expresses the fact that if there is an acceleration, we have a force that changes the motion in that direction. And this is a vectorial equation. As you can see, there are arrows there, so we need to consider the two directions. Luckily, we already have the direction x and z, so this turns out to be a two equation, one in the x, where there is no force, because as I said, in this direction here, there is no force, but there is a component of velocity, which is this one, Vx. Okay, so F equal ml per a times a, and this is Vz. Okay, so in x, Fx is 0, 0 in the direction x. The mass is the mass. The acceleration is the derivative of the velocity of x over time in the direction of x. And we will simplify x and x. The vector, we can remove the vector if you want, because we know that this is the x direction, and I will just say like this, x direction. On the other hand, in the z direction, we have a force, which is the full force in the z direction as well, and then m will be the derivative of v z in the t, and this is direction z. We will remove the vector z, because we know that this is the direction z, and we will just remember that this is direction z. So we have two equations. Of course, how do we solve these equations of motions? Okay, so we have think about the first one. So the first one, it means that velocity is the derivative of the velocity is constant. So the derivative of velocity is 0, meaning that the initial velocity is Vx0, and it doesn't change during the motion. If you want as I said, we can think about this as a way of saying that if the velocity doesn't change, because the derivative is 0, as written here, we can say that the velocity is a constant, which is the initial velocity that it has. So in x direction, the motion is Vx0, and this is the solution of that. This is easy. We can talk through a bit more with math, doing the integral, solving the differential equation, but we can talk through this equation quite easily. So we don't need to do too much math for this. The second equation, though, is still so the derivative is constant, but it's not 0. So the velocity will change, because there is a change of velocity, as we can see, which is due to the acceleration. This is, of course, if there is an acceleration, the velocity will change in time. In this case, we can see that we can simplify the mass, because the mass is in both parts of the sides of equation. Now, this is a simple equation. There is a constant, so if we integrate both sides, we can see that the velocity in g changes as gt equal the velocity vz plus the initial condition vz0. Okay, this is just by integrating this equation between time 0 and time 0. I forgot the fact that we have an interval of time in which we integrate. Okay, so the velocity as time t, so this is the velocity of t, is exactly this expression here, and this is the velocity of x in t. So this is a function of time. This is a function of time is constant. This is a function of time is not constant, as we said. Okay, so why? What can we do more? So we can do, what we can do is to find the roughly the shape of the motion, because at the moment we have a linear velocity, and so I can, if you like, I can uh, erase the equation of motion. We remember them, we simplify them. Now we have other equation of motion if you want, because now we have this can be written as the derivative of x over time, and this can be derivative of z over time. Z is the space, the position, the coordinate, spatial coordinate, and x is the spatial coordinate. So we reduce to study the space now. Now, this is another set of equation for which we can do the same as we did before. We consider the fact that for x we have a constant velocity, so the integral is simple, vx0 times t minus t0, because this is the interval of integration, and x dt is x dt plus x0, and the condition x0 is exactly this condition here. We have it because we have the vector x0, and this is the component x0 of the vector. So we have everything we need to solve the motion in the x direction, which is a uniform motion with a constant velocity. In z direction is a little bit more complicated, because we have so let me highlight this here. In general term, we have what can we do? We have g dt plus g dt 0 minus vz d0 equal derivative of z in dt. Now, as you can see, there are two terms which are constant, which will integrate again. In time, it will be easy to do so, but there is a term which is not constant in time. So this is derivative, if you think about at, derivative of x over t. This is the, well, I mean, I've chosen a poor, but anyway, what I'm saying is that the derivative, it depends on t, so this integral is not is one of the one that we know of, and it will be the square of t divided by 2. This can be derived, simplified, or you can just learn it by heart. Gt square plus gt0t minus vz0t is equal to zt. Okay, and actually we can write this like so. Okay, minus x0 xt. Okay, so this is the bit that we want to highlight, this bit here. As you can see, this is a equation of motion. Well, this is the trajectory, because these are two trajectory and they, as you can see, there is a parabola here in z. We can do the math in the next video, but for now I just want to show that this is a parabola in z and x, meaning that the motion will be following this kind of trajectory. We will give some final equation to estimate what is the angle at which you get the most, let's say, space covered by the projectile, and then we'll see how these be affected by the friction or other components other effect that we neglected. But for now, I guess this is more than enough. So we touch upon how to approach the problem, how to solve two differential equations from acceleration to velocity, from velocity to space, and then we can see that this is drawing a parabola, as is clear from this formula down here. Okay, so let's see what we've got. We have some simple equation for the motion of a projectile, neglecting a few factors, air included, and then the length action will add some of those complications to describe a bit more the real projectile motion, and then we will derive some user for formula to estimate the best shooting trajectory in simple cases. Right, I hope you enjoyed this lesson, and see you next time.